Okay, dear students, so let us see what is there in this video. We have now almost done all the parts. Okay, like the basics are over. You know what is potential, you know what are forces. So let us try to recall each and everything. I'm going to create a table in front of you, and that table, that chart is very, very important to keep each and everything in your mind so that you are not missing anything. That is very important. So whenever you are talking about some kind of a field, this kind of a table is there. So I have already drawn this chart earlier also, but now I am drawing it again. I would be explaining things even better. So the field, first point is that we can understand the field dynamics by considering the forces which are applied within the field. And in the case of gravitational field, let's say, so there is a force, and this is Newton's gravitational force, which is gmm by r square. Now, this is known as inverse square law because it is inversely proportional to the square of the distance between the bodies. It is a central force and all that I have already told you. So the first point is force. So if you want to find, if you want to know, if you want to learn about gravitational field, you can start learning about forces like that. But then you find that this mass m is creating problem for you. So the only way to get rid of this is we defined gravitational field strength, or you can call it G, and it is defined as force per unit mass. So accordingly, we define gravitational field strength and I or G. This can be written as Gm divided by R square, and this depends only on the mass of the central body of the source body, but not on the satellite body. So it could be anything. So whenever, like, we will find this I, you multiply it with the mass of that particular body that you are placing at that point, and you can find the force. Simple. So this is equal to F by m. Accordingly, F is equal to mg or F is equal to F mi. You can say that. Okay. So these are the two things, and we did these things earlier. The units. The SI unit here is Newton, and the SI unit here is Newton per kg. Clear. Now we are moving for the second such thing, which is potential energy. So if you want to study these fields, there is the second method, and that is work energy theorem based. So here we first find the potential energy, and the formula for the potential energy comes out to be equal to this. Now this comes from the definition of potential energy, like what is the work done and all that, and then we do integration, which is not in your syllabus, and after that the potential energy formula is derived. Point to be noted is that for gravitational force is always attractive, and for attractive forces the potential energy is always taken to be negative. That is why it will always be negative. There is no doubt about it. Now, similarly, we want to get rid of the mass m, so we defined another thing, and that is gravitation potential at a point. So that is the gravitational potential at some point, like what this is V1, at this point it is V2. So what is the potential when you keep on moving away from it? Accordingly, you found that V is equal to negative Gm by R. We can clearly see that V is equal to the potential energy per unit mass, or you can even say that we are actually substituting the value of mass m as 1 kg. Even that you can assume, and accordingly you have created two corresponding concepts. I think you understand each and everything up to this. Now in this video, one of the very important topics that we are going to do is the relationship between the force and the potential energy, the relationship between the gravitational field strength and the gravitational field potential. So what is the relation here? So these two things are related with each other by the formula F is equal to negative du by dr. Now capital U is written as potential energy in many places, so that is why don't get confused. U means potential energy. So F is equal to negative of du by dr. Similarly, a similar formula can be created for these things. F will be converted into I, and in place of U we can write V. So that will become negative dV by dr. So I is equal to negative dV by dr. Both of the formulas are equally important. You see, in the case of topic A, I tell you, like when we did A, we learned about a lot of forces there, friction and pseudo force, and so many forces we did: tension, thrust, reaction force. There is one another type of force which is called field force that we have not done in that topic. There are three types of field forces: gravitational force, electrostatic force, and magnetic force. All of the three are following these principles, similar threes, like they all are similar. Okay, and this formula, which is F is equal to minus du by dr, is actually the defining feature of a field force. Like we say, inertial force, F is equal to m into a; friction force, F is equal to mu into n or mu into r. Similarly, field force, F is equal to negative du by dr. So this is actually the defining feature of such kind of forces. Now, from the point of view of gravitation, we have learned about the gravitational force and the gravitational potential energy. They are related with each other by this formula. This formula, it is hot favorite for IB. They create graphs. We would be doing those between the potential energy and R, between the potential and the R, and you are going to comment on what is gravitational field strength at that point or the force at that point. We have to find slope, we have to find area, and all those kind of things. Okay, so this is it. The third formula or the third method that I told you that we will be employing is field lines. So we create field lines also, like gravitational field lines, electrostatic, electrical field lines, magnetic field lines, like that. They are field lines, and we have already done that. There is one video which is already created on this. And at that time, I told you that we will be doing equipotential lines later. So today we are going to learn about the equipotential surfaces, sorry, not lines, surfaces. And electric field lines or gravitational field lines, they are lines, but the equipotential is the surface. Now, we are moving into equipotential surface. So I'm erasing everything here. I hope that you people understand these things. Now, this one thing, this is an example in front of you. What is happening here is we say that the gravitational potential is given by negative gm by r. So whatever the value it be, g is a constant, universal gravitational constant. M is the mass of Earth, which is not going to change with respect to your position in the space. That is not going to change. So technically, these two are constant values. R is the only variable. So potential is inversely proportional to R, which also means that if you are going to fix the value of R, you fix the value of potential. So these are all spheres that they have drawn because Earth is a sphere. So there is a spherical symmetry in gravitation. So each and every, like there are concentric spheres having the same center, but one surface is covered with another. This is covered with even bigger surface. So all these surfaces are spherical with the same center. That is what is happening here. This is the center, and these are all different potentials. So if we are going to consider like these 3 4 points, you can indeed see that for all these 4 points, the radiuses, the radii is the same for all these four, and that is why the potential is also same. So this is called equipotential surface. Equipotential surface. There is another very important point, like point number one, let's say, what is the work done in moving a mass from point one to point two? So we know we did it that the work done is given by the m into delta v. You might remember it. But on an equipotential surface, the potential remains the same. So if you are reaching back to the same radius, like you flying like this, even then it doesn't matter. But at the end of the day, the radius is the same. So if you're moving on this surface or if you're coming back to the surface, the net work done will be equal to zero because actually the potential is not changing at all. A very important point. So no work is done in moving a body on an equipotential surface. So if you move it to the point 3, the work done is still 0. Okay. What are the other important points that we can learn about equipotential surface? Now that is point number 2, they do not intersect, similar to the field lines. Now, the another thing is the relative closeness. The relative closeness depicts the strength of the gravitational field. So it means when the equipotential surfaces are closer together, we can say that the gravitational field is more powerful at that point. Now, what is happening here is, obviously, if I say, like, if you're going to concentrate in this area, in this distance, there will be many equipotential surfaces, but the radius should be the same. The only condition is that the radius should be same. So how can you say that what are the lines? How are you able to control the number of equipotential lines? Because whatever space you consider, there can be infinite radiuses. So how can you say that there will be number of equipotential lines and all that? So how do we do that is, we first define what is the total potential difference that you want. So let us say we want to have 10-volt difference between the two surfaces, and then you can draw all the surfaces. So let's say there is 10-volt between all these readings. Like if you go from the point A to point B, the potential changes by 10 units. If you go from B to C, even then it changes with the 10 points. But we know that the distance between AB is more than BC. Even then, the potential difference is the same. Clear? Now, why is that? So the point number one is, the first point that you need to note about the point number three is that relative closeness depicts greater gravitational field strength, and this is depicting a weaker gravitational field at that point. How can we reach this conclusion? I just gave you a formula. E is equal to negative dV by dr, which if we concentrate on, you can write E or you can write I. If we concentrate only on the magnitude and the average value, we can write it like this. So this is the distance between the two equipotential surfaces, and this is the change in the potential. From here, I can write delta V is equal to I into delta R. Okay. Now delta V is the potential difference between the two surfaces, which we are keeping constant. So if this is constant, which only means that if the electric field, or sorry, the gravitational field strength increases, the distance between the two equipotential surfaces is going to reduce. So they are coming closer to each other. Not that very important point from IB point of view. So if you're feeling some heat here, so no problem with that. But you can watch the video again and try to understand what I'm saying. Like I is equal to delta V by delta R. Delta V is written as I into delta R. Delta V, we are keeping it constant. We are giving it, like, assuming it to be 10 volt every time, which clearly means that where the gravitational field strength is more, the distance between the two equipotential surfaces will be lesser. Lesser is the value of I, more will be delta R. So the distance increases. So this distance becomes bigger and this distance become very small. Okay, so that is a very important point that we have to understand. What other points that you can consider here is that they are always perpendicular to the field lines. Field lines are going to be like this. So the field lines are always perpendicular. Field lines are always perpendicular to equipotential surfaces. Nothing more. It's very easy. Just watch the video again. Try to read your book if there is any doubt that you have, or you can even mention that in the comment section. No problem with that. That's it for this video. This is Professor Varun. Thanks for watching the video. All the best. Bye.